Welcome to another lecture on molecules in motion. We have almost covered most of the things which was supposed to be listed in your contents of the syllabus, but a few things we will take up which was not essentially mentioned in the course content, but it is very much part of the understanding what we have. So, starting with I would like to take up few questions which we have already discussed in detail. Actually, when we were talking about the viscosity of gases, viscosity of liquids, we had a question which we had answered that time. But if you have a take a formal question like this, what is the molecular interpretation as to why the viscosity of a gas is observed to increase with increase in temperature, whereas for a liquid what happens, the viscosity of the liquid decreases as we increase the temperature. We will take two such questions. We are going to answer them and answer them in the form like it. The second question may be in the form of a derivation which we have not taken initially. So, the molecular interpretation when we are talking about gases, what happens in a gas system? Gas, the atom and the molecules are far apart. Okay, we can consider it as the system as a very dilute system, and on the average the molecules are very distant apart. So, they are supposed to be only coming closer when they collide. Okay. So, whatever resistance they have in their flow, so viscosity is the measurement of measure of the resistance it experiences while it flows. Okay. So, whatever resistance it is offered in the flow of the molecules is going to be there in the gaseous system is only because of the collision between the molecules. Okay. So, essentially we should understand what is the reason of say viscosity in a gas. Viscosity, gas is free flowing. So, how do we justify having viscosity? The viscosity is only when applicable or can be thought to be as existing because we are considering the collision of particles. So, viscosity arises because the gas molecules undergo collision. Okay. So, from the expression of collision frequency, I will not go into the detail of the derivation, but I have given you the expression of the collision frequency Z. Collision frequency for a given volume of a container, the frequency of the collision which is going to occur is going to be increasing with increasing temperature. Okay. As you see, this is the expression for the frequency of collision. The more the number of collisions we have, the more the resistance, so viscosity should increase. Okay. So, what happens when you having a high temperature? We are saying that viscosity of the gas increases with increase in temperature. That means when I increase the temperature, the number of collision increases. Okay. So, the frequency of collision should be increased, right. So, this is the frequency of collision expression. This is the cross section of collision cross section, which is equal to pi d square, where d is the distance between the two centers, half the distance between the two centers of the atom or molecule which is colliding and supposed to be in touch with each other, and this is the relative speed, and this is the number density of the particles which we have. So, number density, if you remember, we had taken number density as number of molecules in the volume which is contained. This is the definition of number density. And if I want to consider say the total number of molecules, well, then I multiplied the moles into the Avogadro number by the volume, Now this volume which is fixed, I replace it from the equation of PV equal to nRT, and if I replace that by PV equal to nRT, I get something like this. So I have this expression of N in which I put P by kT. So you see, T is in the denominator. Despite that, we have an increase. This is the frequency of collision. We have an increase in number of collision with increase in temperature. Okay, that should be since it is inversely proportional, it should not happen that way. But then how do we justify the increase in collision, increasing frequency of collision with increase in temperature? What is important here, you see, in this expression, what is important here is the relative speed. What is relative speed? If you remember, when we had taken the molecules to be identical, then the relative speed was given to be under root into the mean speed. So the mean speed is given to be 8 kT to the power half by m into pi. This m becomes reduced mass when we have molecules which are colliding are having two different masses. For simplicity, we have considered the gas of one type. So all the molecules are similar. So we have taken this m as just m, and we have got the under root 2 here in the calculation of the relative speed. So what happens is, the relative speed you see has a t term, and this t term is associated with the speed associated with the molecules which are moving. So as you increase the temperature, what happens? The molecules start moving, they have higher kinetic energy, they start moving with a higher speed. So when you have higher speed, the chances of collision becomes increased. So the increase in temperature increases the number of collisions which is the gas molecules are undergoing, and hence it is apparently increasing the resistance to the flow of the gas molecules. So we can say that it is actually increasing the viscosity of the gas with increase in temperature, right? So the whole thing comes from the concept of collision, and collision is going to be related to the relative speed of the molecules which we are considering, and each of them has a temperature factor directly in the numerator. Okay, so this being the reason for the gases. What happens for the liquids? In liquids, what happens? We say that in liquids the viscosity decreases with increase in temperature. And what is the viscosity? It is the resistance to the flow of the fluid system. Okay. In liquids, what happens? On the other hand, the molecules are much closer to each other, which results in a strong attractive forces within the molecules or atoms. Okay, so these since we have strong intermolecular forces in the form of attraction, that causes them to move apart. As you increase the temperature, what you are giving them sufficient kinetic energy to overcome these attractive forces and are able to move freely. So if they are moving freely, that means the resistance is reduced, that means the viscosity is reduced, right? So what happens when in liquids, when you increase the temperature, the molecules which are held together by intermolecular attractions gain sufficient amount of energy to overthrow the attractive forces existing between the molecules, and they start moving more freely. And that even since they start moving more freely, that means the resistance to the motion of the molecules are decreased, that means the viscosity of the system is decreased, right? So this is one of the questions which I was talking about. Next one is, we have not taken up this in the previous classes. This is the question is, you do not get theory question, but this is an important part of the discussions we had previously. We have omitted this discussion, and now I think is, since it's part of some questions which you have in some books, so it is better to at least visit them, in spite of the fact that you already know the expressions, and you should be knowing the expressions. Go through the slides, you will see the expressions. So what we are going to be looking into the next question is derive the expression for diffusion characteristics or diffusion parameters, specifically the diffusion coefficient d, the thermal conductivity kappa, the viscosity coefficient eta for a perfect gas on the basis of kinetic molecular theory. So if you remember, in the kinetic molecular theory, we had stopped the discussion on just having the phenomenological equations. We did not go to derive the constant parameters which we obtained in the phenomenological equations. What we had given you is this table, in which each of the properties was mentioned, what was being transported in that particular process was also mentioned, and the diffusion parameter or diffusion characteristics, the constant which was obtained from the phenomenological equation was just taken to be d kappa eta. We had taken that we will assume these are the equations. We have discussed these relationships, but we have never derived these relations. We have said that this is not going to be discussed, we will take these to be known to us. But when we are talking about a course which is covered so much, I think it is very relevant that we talk about how do we derive these diffusion parameters or diffusion characteristics for each of the cases, like in diffusion coefficient, thermal conductivity, viscosity coefficient for a perfect gas, using the same thought and processes which are arguments which we had while discussing the kinetic theory of kinetic molecular theory. So what we can recall, we have summarized these expressions of diffusion parameters of a perfect gas using kinetic theory, but have not derived these expressions. Now let us do the derivation right now. Have a look at these expressions. These was tabulated previously. For a diffusion process, the matter transported was the molecules, the quantity transported was matter or molecules, and that condition for which we have the phenomenological equation satisfied, we had said that the proportionality of constant was known as the diffusion constant d, which was given to be 1 by 3 lambda c bar, that is relative speed, mean relative speed, and this is lambda is the mean free path. Similarly, we had said for a property like thermal conductivity, the quantity which was being transported was energy, and the phenomenological equation, the constant in that phenomenological equation was taken to be kappa, that is the thermal conductivity coefficient, that was given in terms of C1 by 3 lambda mean relative speed into CV molar specific heat into the concentration, molar concentration of the gas molecule. So similarly, we had for the viscosity, we have 2 or 3 expressions. You just have a look. We are going to now visit this and see whether we are going to get these expressions from the logics which we had applied for other systems, or we have even in the discussions of the kinetic theory of gases. So what happens? What for the viscosity property? If the property is viscosity, what is getting transported is linear momentum. What you have the phenomenological equation was a gradient in velocity, and the x component of the linear momentum was proportional to the velocity gradient in the z direction, and that was given to be the constant of proportionality was given to be the eta, the coefficient of viscosity. So, we are going to be looking into each of them. Let us begin with the diffusion, since this is the most fundamental, and once you understand the logics with how we derive the expression for diffusion of matter, it is only going to be the concept will remain same as to how we derive the transport of energy and transport of linear momentum. Only thing is the factor which is where we are talking about number of molecules, or the number of molecules or number density in case of transport of matter. Here each of the molecules will have some associated energy. So, along with the number of molecules which is involved, we have to take into account the associated average energy for that molecules. Similarly, when we are talking about the number of transfer of linear momentum, we need to know the number of molecules and need to multiply them with the total number of linear momentum which we get, multiplied by the total number of molecules present, will give you the average amount of the viscosity, average amount of the linear momentum which is being transported. So, these are the three parameters which we are going to look into. Let us begin with the diffusion. For derivation of the diffusion coefficient d for a perfect gas, just have a look at this diagram. What does the Fick's law say? Fick's law says that the gas molecules or matter will move from a region of higher concentration to a region of lower concentration. From high concentration, the movement will be always towards the low concentration. So, for calculating the rate of diffusion of a gas, let us consider a net flux of molecules through a plane A0. This is the A, which is the window which we are looking into. We are going to see the net flux of molecules which is passing through this area A as a result of arrival from a distance, say lambda and lambda minus. If this I take it as the axis as 0 along the z axis, it can be x, y, z anyway, but if I take along say I consider this as z axis, what I am considering is to find out the rate of diffusion. What I am doing is I am trying to find out the flux of molecules through which is passing through this area A or A naught as a result of arrival from a distance of lambda in each of the direction. Lambda is the mean free path, it is the distance travelled after a recent collision. After the last collision, what is the distance travelled? So, what I am saying is after the collision, the molecules that has travelled lambda distance is reaching this. Okay. So, similarly, molecules here reaching is only a distance which is equal to 1 lambda is coming from this side as well, either from right side, this is the right side, we are moving towards 0, or from the left side we are moving towards 0. Now, consider this projection in this graph. This is the graph where you have the number of particles or number of molecules in the y axis, and z axis is corresponding parallel, consider parallel to the one which we have here. So, consider if I project this as parallel to the window of this our interest, if I project it on this this graph of n versus x, which is the number of graph between the number of particles or moles with their distribution with the z axis. So, if I project this and I call this, since this I have marked as 0, I mark this as 0. Okay. So, the number of particles or molecules, the number density of molecules at 0. Okay. So, let us take this as the origin. Now I can consider how many molecules are crossing this window and reaching this place. And suppose the molecules are moving with the mean relative speed c bar. So they are in delta time t. So the distance they cover is going to be c bar delta t, and the total volume contained in this area will be the area into of the interest window into c bar delta t, because that is the distance. Delta velocity equal to distance by time. So if I want to find out the distance, I multiply time into the velocity, I get the distance. So if the molecules are moving with the mean speed, relative mean speed c bar, then I multiply with the interval in which they have traveled, delta t, and this delta t into c bar gives me the distance traveled, and this distance is this one, and in this area and the total volume element will be this area into the distance traveled c bar delta t. So A into c bar delta t is the total volume element of interest which we are looking into. Okay. So on the average, molecules passing through A at 0 has to travel one mean free path lambda since its last collision. So I have assumed that to reach the window, I will consider only the molecules which undergo one mean free path distance. Okay, that is 1 lambda since the last collision. So the number density they are where they are originating, let us say nz evaluated at z equal to minus lambda. What do we get? We get the number of the number density originated at z equal to number lambda minus lambda can be given by a Taylor expansion series, where this is at 0, number density at 0, lambda equal to 0, minus the lambda into the gradient of number density and into x. Like if you are taking a Taylor series, if you want to take a Taylor series, if you have a function like this and you want to evaluate the value, then function fx is equal to fx value when x equal to at 0 or the origin plus the first differential of the f with respect to the variable into the variable. So and truncating the other values, if I compare these two, compare that to that the number of molecules, then I can write down the number densities at a distance 1 mean free path away from the origin of the center of interest or window of interest is given to be the number density at minus lambda. Minus lambda means at this location. That means we are going, the particles are going from this side to left side to right side. And if you see left side minus lambda correspond to this. Okay. So minus lambda corresponds to this, means the concentration or number density of this position is going to be higher than this one. Okay. So if the number density of the molecules is going to be higher at this one compared to this one, then what will happen? The molecules will tend to move from higher to lower. So when I move from higher to lower, what I am moving? I am moving from actually the, if you take this left side, you are taking and this side as right side, then you are moving from left to right when you are going towards the window. Okay. So when we are going towards the window from the left side to the right side, then actually what we are moving is we are moving from a higher concentration of the number of molecules to that of the lower concentration. And mind you, we are only considering the molecules which are going to undergo only one mean free path distance to reach the window of interest, that is A. So, all distances means this distance which they are going to transfer is going to be considering only one mean free path distance, not beyond that. Okay, we are not talking about multiple integers of the mean free path. We are talking about the number of molecules which have undergone one collision, and the minimum collision is it has undergone at least one collision before reaching the which is going to reach make one collision to reach the window of interest. I don't know whether I am able to make you understand. What we are saying, that on the average the molecules passing through the area A at z equal to 0 have to travel at least one mean free path, that is since the last collision. That means if you have the last free path having at any time and the molecules are still surviving and not gone lost its energy, then it has to minimum travel one mean free path, lambda distance, to reach the window of interest. This distance is lambda. Okay. So, this is the mean free path. That means the distance traveled between two consecutive collisions. If I have this last collision, it happened sometime, and the next collision is going to happen here, then I say the mean free path here is going to be lambda. Okay. So, this is going to be the next collision, and then this was the time where it was previous collision. The distance it traveled from previous collision to the next collision is known as the mean free path. So, this distance is what we are going to be interested, and that should be one mean free path, means it should be colliding only once since the last collision. Okay. There should not be any shorter collision, or there should not be any longer collision. The distance should be to the average value of the should be equal to the mean free path of the molecules, right. So, having understood that, I hope you have understood that for calculating the rate of diffusion of a gas, let us consider the net flux of molecules which is passing through the area of window of interest of area of window of area A as a result of arrival from an average distance lambda. This average distance is one mean free path away from the last collision, away from each direction, and where lambda is the mean free path. On the average, the molecules pass through the area A at z equal to 0 have travelled one mean free path since their last collision. Therefore, the number density which they originated can be given to be in terms of is something like this, in terms of the Taylor expansion series. So, Taylor expansion series is given at the number density or any function at a given location is going to be the function at the origin minus or plus, depending on what type of function you are taking. It will be minus or plus the position of that distance which where you have traveled into the slope of the change of the function with the distance. So, if I have this expression applied to that of the number density, then number density at a location where z equal to minus lambda is equal to the number density at z equal to say condition where z equal to 0, and will be minus the slope of the change of number density with distance into the lambda, which is the distance which is travelled between the consecutive jumps. Okay. So, if I have this change in the number of molecules, then I can rewrite this as the number density which originates at x z equal to minus lambda, and can be approximately by using the approximation of truncated Taylor series expansion. We have the n lambda at z equal to minus lambda will be equal to the number density at x equal to z equal to 0 minus what is the slope of the number density with the distance z into the distance it is travelled. And what is the distance travelled? Distance travelled is lambda. Okay, we could have written this as x, but we know the distance which is it's travelling is lambda. Okay, so the number of impacts on an imaginary window of area A in time interval delta t is given to be ZW. You have to look into the collision frequency and other things. The number of impacts of imaginary on the imaginary wall of area A is in time delta t will be nothing but the say z whatever ZW on the hitting on the wall into A0 into AT. Okay, where ZW is nothing but 1 by 4 number density into the mean relative speed. Okay. So, the flux of molecules moving from left to right, say what is this left side? This is the left side. Left to right, assigned from supply of molecules from left, that means from higher concentration to lower concentration, will be given as you see the flux is always going to be this divided by A into delta t per unit area per unit time. So, this is the number of molecules which is travelling. What is the number of they are travelling with the speed the mean speed of c bar into the distance into delta t is the distance, and what is the area? This is the area, and what is the number density which we have? We have the number density at lambda minus equal to n minus. This is actually signifying the number density at minus lambda. So, that is nothing but 1 by 4 n at lambda minus into the relative mean speed, right. So, today we are going to be ending the section here. I think I need to take up this a little bit more in detail, so that we can complete all the diffusion parameters in a perfect gas. Thank you so much.